So today it's my particular pleasure to introduce Gabriele Benomio. Gabriele completed his PhD at the Department of Mathematics at the Imperial College of London, and he is currently an associate research scholar at Princeton University's Gravity Initiative. His research interests include analysis of PDEs and general relativity. So please, Gabriele, the floor is all yours.
Thank you very much. Can you see my slides?
Yeah.
And my cursor as well?
Yes.
Okay, good. Okay, so thank you very much for the invitation. It's of course a pleasure to give this talk today, and it would have been probably nicer to be in Cambridge and give this in person, but I'm sure we find occasions in the future to meet and chat in person. So today I'll be telling you about a theorem that I prove as part of my PhD thesis. But given the rather broad audience that I think I have today, I'll try to avoid most of the mathematical technicalities and details and give more a sort of an overview of the result. Okay, so let me start with an outline of what I'll be talking about. So the vacuum-Einstein equations and general relativity can be formulated in 4 dimensions as well as in higher dimensions. So I'll start by reviewing some well-known facts about the vacuum-Einstein equations, black holes, and their classical stability, both in 4 and in higher dimensions. And in particular, we'll be interested in comparing the stability properties of 4-dimensional black hole solutions to those of higher dimensional black holes. So while in 4 dimensions, all stationary vacuum black holes are expected to be described by the Kerr family of black holes and to be classically stable. In higher dimension, there exists a whole zoo of new stationary vacuum solutions, and some of these new solutions are expected to be unstable. So to better understand these novel properties of higher dimensional GR, we restrict our attention to a particular family of unstable stationary vacuum black holes in higher dimensions called black rings. So after reviewing some of the known instabilities for this family of black holes in the second part of the talk, I claim the existence for a new instability for the spacetimes and describe its main features. So this instability will be new in the sense that it's never been observed for black rings or for other higher dimensional spacetimes. But probably even more importantly, it will be for the first time in the context of black ring instability supported by mathematical theorem. And this mathematical theorem will appear in the second part of the talk. So the third part of the talk will be about the claim that this new instability may be seen as the manifestation of a more general instability affecting a more general class of spacetimes that go beyond black rings and other higher dimensional black holes. So the third part of the talk will be about trying to make sense of this claim. And if I have some time left, I'd also like to tell you some of the ideas and methods involved in the proof of the theorem. Okay. So let's move to part 1. So we'll be interested in the classical stability of black hole solutions to the vacuum Einstein equations, ρ(g) equal to 0. So let me stress that everything I'll be saying will be classical and will be restricting to the exterior region of black hole solutions. So I won't be saying anything about black hole interiors. So as we all know, a solution to the vacuum Einstein equations is a spacetime mg, where we allow the dimension n of the spacetime to be greater or equal than 3+1. So we'll be restricting to vacuum, and we set the cosmological constant to be equal to 0. So if one chooses coordinates on this spacetime mg, the vacuum Einstein equations become manifestly a system of second-order partial differential equations. And if coordinates are constructed in a proper way, such a system of second-order nonlinear PDEs becomes a system of nonlinear wave equations. And the system turns out to admit a locally well-posed initial value problem. So the relevance of the initial value formulation and this of general relativity and this well-posedness is that it gives the mathematical framework to study the dynamics and in particular the stability of solutions to the Einstein vacuum equations. So as I told you in the outline of the talk, we'd be interested in the stability problem in higher dimensions. But before moving to that, let me recall what the picture looks like in the usual 3+1 dimensional setting. So the stability problem for the vacuum Einstein equations in 3+1 dimension. So the nonlinear stability of the trivial solutions to the 3+1 dimensional Einstein vacuum equations, namely Minkowski space, has been established by the celebrated work of Christodoulou and Kahneman, and still remains a very active area of mathematical research. While the nonlinear stability of the subextremal Kerr spacetimes remains as a mathematical conjecture still open, and there has been a lot of recent progress on both the linear stability and nonlinear stability problem for Kerr. And as we all know, the Kerr stability conjecture may be understood as sitting within a larger and more general conjecture called the finite state conjecture, which also claims that the Kerr family is describing all stationary vacuum black holes, and thus characterizes all the possible stationary end state of black hole dynamics. So although we'll be mainly concerned with the case of zero cosmological constant, let me also recall the main features that one see when the cosmological constant is negative. So in the case of the vacuum Einstein equations with negative cosmological constant. So now the trivial solution is called anti-de Sitter, and once reflective boundary conditions are assumed at infinity, anti-de Sitter is expected to be nonlinearly unstable. The same being true for the family of Kerr-ADS black holes. Once again, reflective boundary conditions are assumed at infinity. So I should stress the boundary condition, the kind of boundary conditions that one assumes are important. And in fact, if different boundary conditions are assumed, like for instance, the sympathy boundary conditions, then anti-de Sitter and Kerr anti-de Sitter spacetimes can be expected to be nonlinearly stable. Okay. So let's now move to higher dimensional general relativity. So higher dimensional GR is of course very interesting from the point of view of theoretical physics, but let me also stress that from the pure mathematical perspective, it is interesting to try to understand whether properties of solutions to a certain system of PDEs, like for instance in our case the vacuum Einstein equations, depend on the number of dimensions that one considers. And this is indeed the case for the vacuum Einstein equations, and it turns out that the dynamics of solutions in higher dimensions is richer than the dynamics in the 3+1 usual setting. And most of these new features of higher dimensional general relativity already show up in 4+1 dimensions, meaning just one dimension higher than the usual 3+1 dimensional setting. And the two main features that one sees in 5-dimensional general relativity are the following. So the first is a failure of rigidity. So remember that I told you that for 3+1 dimensional GR, one expects that all stationary vacuum black holes are described by the Kerr family. While in higher dimensions, there exists multiple families of stationary asymptotically flat black hole solutions. And to better understand how this family look like, in the next few slides, I'll show you some examples of these new families. So let me also say that in higher dimensions, it's possible to obtain non-asymptotically flat solutions by multiplying the usual 4-dimensional space-times by an extra compact dimension. Like for instance, one can obtain 3+1 dimensional Minkowski times S1, and multiplying the 3+1 dimensional Schwarzschild or curved black holes times S1. And the second examples are usually known as black strings. And the spacetimes are usually referred to as being asymptotically Kaluza-Klein because of the presence of this compact dimension. So the second new features of higher dimensional general relativity is that some of these new families of stationary vacuum black holes are expected or have been shown to be classically unstable to gravitational perturbations. And this should be contrast with the conjectural, if you want, stability of the Kerr family in 3+1 dimensions. Okay, so let's now move to some examples of these new families of stationary asymptotically flat black holes. So the perhaps most elementary extension of a four-dimensional black hole to higher dimension is the case of the Schwarzschild, of the family of higher dimensional Schwarzschild black holes. So this family can be formulated in any dimension greater or equal than 3+1, and was first written down by Tangerlini in this paper from 1962. So this is a one-parameter family of matrix parameterized by the mass of the black hole, and its Schwarzschild coordinates read as follows here. So you see that you still see the usual matrix coefficients that you have for the four-dimensional Schwarzschild matrix, but one has to replace the radial weight by some appropriate power depending on the number of dimensions that you consider. And the d omega squared here that you see here is the standard matrix on the unit n-2 dimensional sphere. So this is a family of static spacetimes, and they have spherical horizon topology, meaning the cross-section of the horizon is a Riemannian manifold with spherical topology. And this family is expected, as for the four-dimensional case, they're expected to be stable. Now, a far more challenging task is to try to find a higher dimensional example of a family of stationary rather than just static black holes. And this was first achieved in this remarkable paper by Myers and Perry from 1986. And this new family that they constructed is now known as the Milesperry family of black holes. So this can be constructed in any number of dimensions greater or equal than 4+1, and should be thought as the higher dimensional generalization of the Kerr family. So this is a family of stationary rotating black holes, but the black hole can have two or more axes of rotations. And when the rotational parameters are set to be equal to 0, this family contains the Schwarzschild, the family of n-dimensional Schwarzschild black hole. So this one parameter family should be thought as sitting within the larger family of stationary Milesperry black holes. So as for the case of Schwarzschild black holes, Milesperry black holes have spherical horizon topology, and at least in some parameter regime, these black holes are expected to be non-linearly stable. Okay. So now note that after you know about the existence of this family of Milesperry black holes, one might, in principle, entertain the idea that all stationary vacuum black holes in higher dimensions are described by the Milesperry family of black holes, in strict analogy to what one sees in 3+1 dimensions with the Kerr family of black holes. But such an idea fails spectacularly in light of this paper by Emparani and Rial. So Emparani and Rial in 2002, they discovered the first example of a stationary asymptotically flat solution with event horizon of non-spherical topology. So this new family is called the family of black rings, and was originally formulated in 4+1 dimensions, and really should be thought as an independent family from for instance, the family of 5-dimensional Milesperry black holes. And in fact, they have a different horizon topology, so they should be seen as completely completely independent. So these black rings first constructed by Imparani and Rial, they have been then generalized to more complicated and more general black ring spacetimes by some later works. So these black ring spacetimes, that will be the main object of the talk. So let me maybe spend 5 or 10 minutes discussing the main features of this spacetime. So this is a family of two parameter family of solutions, where the two geometric parameters characterizing the metric can be called R0 and capital R, and they have to satisfy this bounds here. So I'll tell you in a second what's the meaning of these two parameters and how one should think about them. So this is a family of explicit, stationary, and asymptotically flat spacetimes. So let me stress that they are truly asymptotically flat, so they don't possess any compact dimension. So they're asymptotically flat, if you want, in the same sense the curve is asymptotically flat. So the event horizon has cross-sectional topology S1 times S2, which motivates, if you want, the name black rings given to this family of spacetimes. So now one can interpret these two parameters in the following way. So R0 can be thought as the radius of the S2 at the event horizon, while capital R can be thought as the radius of the ring. Okay. So this family has no analog in 3+1 dimensions, and it also determines a failure of rigidity. So a failure of both the topological rigidity that one sees in 3+1 dimensions, where black holes need to have spherical topology, and it also a failure of rigidity within the family of higher dimensional stationary vacuum black holes, because we know that in addition to this black ring family, there also exist spherical black holes, like for instance the Milesperry black holes. Okay. So the stationary black holes, they possess an angular rotational velocity that here I call omega, and this should be thought as being a velocity along the S1 of the ring, and the velocity parameter is constrained, is fixed once these two geometric parameters are chosen, and this explains why this is really a 2-parameter family rather than a 3-parameter family of spacetimes. So the angular velocity should be thought as balancing the ring against its tendency to collapse under its gravitational self-attraction, and is therefore determined by the thickness, if you want, of the ring. So once you fix these two parameters, then the ring has to have a certain precise rotational velocity to stay in balance. Okay. And the family of black rings can be informally divided into two subfamilies. So one is usually called the family of thin black rings, when the radius of the ring is much larger than the radius of the S2 at the horizon. So a thin black rings really looks like the one that we have here in this picture here. While fat black rings are black rings where the two geometric parameters are of comparable size. So the ring looks more like a donut, if you want. Okay. And thin black rings, because of this constraint that I told you about on the angular velocity, they're also automatically slowly rotating black rings. Okay.
Can I ask a question?
Sure. Yeah.
With R not bigger than R, do you run into naked singularities, or does it just come together and then form a topologically sphere horizon rather than the topologically ring horizon?
The honest answer is that I don't know, but yeah, I mean, I should say that so the black ring family doesn't, so if you want, doesn't contain a spherical black hole in the limit that R0 goes to capital R. So you don't, if you want, you don't. So spherical. So if you want, so if you push R not to capital R, you don't get a Milesperry black hole. That's what I'm claiming.
Mm-hmm.
I don't know how one should understand such a limit.
Thanks.
Yeah, no worries. Oh, okay. So from the dynamical point of view, the fundamental fact is that all black rings are linearly unstable. Okay, so these have been shown in many heuristic or numerical works, and the nature of the instability that affects a black ring depends on the values of these two parameters. So the claim is that for any choice of these two parameters, the black ring that you get will be linearly unstable, but the nature of the instability that affects the black ring depends on the values of the parameters. So for very thin black rings, so remember black rings that look like, if you want, the one here in the picture, the instability is driven by the so-called regular Flam mechanism that has first been observed and studied for Schwarzschild black strings. So for 3+1 dimensional Schwarzschild times S1. So the existence of the regular Flam instability is a claim about the existence of an exponentially growing mode solution to the linearized Einstein vacuum equations. So it's a linear instability because it arises at the level of linearized gravity. And it's a gravitational effect because it arises really for metric perturbations. Okay. So as I told you, black rings have all been, so black ring instabilities have all been discovered and discussed in numerical and heuristic works. So the aim of my work was to try to prove a first mathematical theorem suggestive of a dynamical instability for this family of black holes. Okay, and this ends the first part of the talk. Maybe I should pause a second and see if there are any questions. No?
Yeah. Do you have a quick explanation for why black rings are not possible in 3+1 dimensions?
Sorry, could you repeat the question?
Is there a quick reason for why these black rings are possible in 4+1 but not 3+1 dimensions?
Yeah, I think that should be thought as constructed from considering a 3+1 Schwarzschild times R and then closing sort of the black string in a loop. So it should be in a number of dimensions where in principle you should first be able to construct a black string, then close it and then give some rotation to the black hole, I think.
But you also could view 3+1 dimensional space as like circle fibered over lower dimensional space, and then you could still have BTZ black holes in 2+1 dimensions, right?
Yeah, I'm not familiar with this BTZ.
But if you took the very long limit of a black string, you'd get, if you had one in 3+1 and you took a very long limit where it was long straight one, that would give you an asymptotically flat black hole in 2+1, and we don't know those. We know those don't exist.
Mm. Okay. Yeah.
Okay. Okay, so maybe let me move on. So the theorem that I ended up proving is indeed suggestive of an instability for black ring spacetimes, but is in fact suggestive of a new instability for black rings, meaning that is suggestive of an instability that has never been observed before for this family, neither for other higher dimensional spacetimes. So this instability is expected to affect very thin black rings. So like the one I showed you before in the picture. And it has the following four main features. And we spend the rest of this second part of the talk trying to understand better these four features. So the first one is that this instability is for the first time in the context of black rings instabilities supported by a mathematical theorem. It is a nonlinear instability that is already manifest at the level of scalar perturbations. So maybe for people familiar with this kind of problems, let me say that I really mean that this instability would be already manifest at the level of systems of nonlinear wave equations, where the nonlinearity satisfies certain good structural properties, like for instance the null condition, that tell us that these are good models for the Einstein vacuum equations. Okay. And this new stability can be ascribed to a precise geometric property of very thin black rings. So these I believe are the main features. So let me start by telling you about this geometric property. So this key geometric property has to do with the null geodesic structure of black rings, and in particular with the presence of geodesic trapping. So geodesic trapping is a phenomenon that we are familiar with because it already occurs on Schwarzschild or on Kerr black holes. But in the case of black rings, it occurs with some important differences. So let me remind you that in the case of Kerr, when one studies geodesics, can separate the Hamilton-Jacobi equation and reduce the study of geodesic motion to the study of radial motion of non-geodesics. And by doing that, you obtain a one-dimensional effective potential that tells you how radial geodesics move. So this potential turns out to admit an extremal point, which corresponds to a geodesic traveling a fixed distance from the Kerr event horizon. And such an extremal point is a local maximum, which corresponds to the statement that trapping for Kerr is unstable. So if you vary ever so slightly the initial condition of the geodesic, so its position or velocity, the geodesic will either fall into the black hole or escape to null infinity. So as I told you, geodesic trapping occurs for black rings as well, but for very thin black rings, there are some new and important features. So first, the Hamilton-Jacobi equation does not fully separate. So the best you can do is to reduce the study of geodesic motion to a two-variable ODE. Where now this potential, the effective potential, still admits an extremal point, but such an extremal point can be a local minimum. And this corresponds to the statement that null geodesic trapping in the case of very thin black rings can be stable. So this means that if you perturb a little bit the initial condition of the geodesic corresponding to the minimum of the potential, you will obtain a geodesic that travels for all values of its affine parameter in a confined bounded region in space outside the black hole. Okay. So this is a surprising phenomenon. And let me stress that for stationary asymptotically flat solutions to the Einstein vacuum equations, it is a novel and, as I said, perhaps surprising feature of higher dimensional general relativity. Okay. So, and because it's surprising, let me give you maybe a brief heuristic of why this stable trapping appears in very thin black rings. So the local geometry of very thin black rings resembles that of 3+1 dimensional black strings. So here, note that in this slide, I'm mentioning both rings and strings, okay? So the local geometry of very thin black rings resembles that of 3+1 dimensional Schwarzschild times S1 black strings. And 3+1 dimensional Schwarzschild black strings that meet stably trapped null geodesics on their exterior. And if you want an intuitive explanation for this to happen, is that massless particles with some non-vanishing momentum along the S1 of the black string they roughly move as massive particles in the exterior of a 3+1 dimensional Schwarzschild black holes. So the claim that there exists stable time-like circular orbits on the exterior of a 3+1 dimensional Schwarzschild black hole should be seen as implying the existence of stably trapped null geodesics on the black string exterior. And this in turn tells you that you should expect this stably trapped null geodesic appear in the very thin black ring geometry. Okay. So why is geodesic trapping relevant to understand stability and instability of spacetimes? Well, that's because trapping is a geometric property of the spacetime that interacts with high frequency components of perturbations. So in the regime of the optic approximations, one should think of high frequency perturbations as traveling in the proximity of null geodesics for a very long time. And this should be seen as an abstraction to dispersion of perturbations. So this abstraction to perturbations already occurs at the most basic and fundamental level, meaning at the level of linear scalar perturbations. So scalar fields satisfying the linear wave equation. And why is this particularly relevant for us? Well, remember that at the start of the talk, I told you that the vacuum Einstein equations can be formulated as a system of nonlinear wave equations. But such a system, because of its nonlinear and together tensorial character, is very difficult to study from the pure mathematical point of view. So a good toy model to start with and to try to gain some intuition about the nonlinear dynamics of the vacuum Einstein vacuum equations. A good toy model is the initial value problem for the scalar linear wave equation. And if one is interested in the nonlinear dynamics of solutions to the Einstein vacuum equations, one typically tries to understand decay, or if one dispersion of solutions to the linear wave equations. And it turns out that to opt for nonlinear stability of solutions to the Einstein equations, good dispersion, meaning fast decay in time, at the linear level is key, is crucial. Okay. So now it turns out that although trapping should be seen as an abstraction to dispersion, one should expect to still be able to prove decay for linear scalar perturbations in presence of trapping. But whether fast decay can be proven, that heavily depends on the nature of trapping that you have on the spacetime. So from this point of view, the nature of trapping is crucial. And by nature, I mean whether trapping is unstable or stable. Okay. So this is conceptually probably the most important slide of the talk. So if you have any questions, you should stop me and ask me. Okay. So to clarify this, let me go back quickly to the case of Kerr black holes. So remember that I told you that in the case of Kerr black holes, we do see trap null geodesics, but trapping is unstable. And they claim that unstable trapping is compatible with fast decay of linear scalar perturbations. And it's not just compatible, but it is a theorem by Dafermos, Rodiansky, and Schrappett-Rothman. The linear scalar perturbations of subextremal Kerr black holes decay fast in time. And they're also able not to just say fast, but to give some quantitative statement to the decay rate. So linear scalar perturbations have to decay polynomial in time on Kerr black holes. And it turns out that this decay rate is sufficiently fast to prove stability of Kerr to nonlinear scalar perturbations. And this is suggestive, if you want, and motivates in part the Kerr stability conjecture. So it motivates the expectation that Kerr is nonlinearly stable as a solution to the full nonlinear Einstein vacuum equations. Okay. So let's now go back to our very thin black rings. So in the case of thin black rings, I told you that trapping is stable. So in the presence of stable trapping, one should think of perturbations that are being trapped in some effective potential well. So decay can still, or if you want dispersion, decay can still occur, because or thanks to the tunneling effect. So the energy of the perturbation, if you want, can tunnel through the potential barrier. So you can still observe some sort of decay, but dispersion will be weaker than in the case of unstable trapping. So from the dispersive point of view, stable trapping is much worse than unstable trapping. Okay. And this motivates the fact that stable trapping may force slow decay of linear scalar perturbations. Okay. So the theorem that I prove, and this is the main statement of the talk, is that this is not just a possibility, this slow decay of linear scalar perturbations, but it is indeed the case that for very thin black rings, the presence of stable trapping forces linear scalar perturbations to decay slowly. So the statement of the theorem is that linear scalar perturbations of very thin black rings cannot decay fast in time. And this is the statement that motivates the expectation that we have a nonlinear instability coming from the slow decay of linear scalar perturbations. And remember that this slow decay should be ascribed to the presence of stable trapping on this spacetime. So the first maybe remark is to note the contrast that this statement, to contrast this statement with the behavior of linear scalar perturbations on curved black holes, where you have fast decay, and in general with the expectation of stability for the 3+1 dimensional stationary vacuum black holes. Okay, so as in the case of the theorem by Dafermos, Rodiansky, and Shapeto-Rothman, my theorem also comes with a quantitative, if you want, statement. So the quantitative statement is that linear scalar perturbations of very thin black rings cannot decay faster than logarithmically in time. Okay, so logarithmic decay is regarded in general as slow decay. So, and this is why here I said that linear scalar perturbations cannot decay fast in time, because we know that they cannot decay faster than logarithmically, and this logarithmic decay rate is regarded as slow. So one expects the logarithmic decay at the linear level is not enough to prove stability results for nonlinear scalar perturbations, and is therefore suggestive of a nonlinear instability. And this quantitative statement should be contrast with the polynomial decay rate proven by Dafermos, Rodiansky, and Shapeto-Rothman in the case of curved black holes. Okay, so this is the theorem. So a last slide in the second part of the last slide of the second part of the talk. I want to go back for a second to something that I told you before about the instabilities of black rings. So remember, I told you that thin black rings are affected by a linear gravitational instability called Gregory-Laflamme instability. So now I want to stress that this new instability that I discuss is really a very different thing from the Gregory-Laflamme mechanism. And then the presence of this Gregory-Laflamme instability a priori doesn't tell you much about the existence of this new instability that my theorem suggests. Okay, so let me contrast maybe some features of the Gregory-Laflamme instability with my new instability. So I told you before, in the case of black rings instability, my instability is supported by mathematical theorem, while in the case of the Gregory-Laflamme instability, there are, if you want, some numerical simulations, but there's no rigorous treatment of the instability. So our new instability is a nonlinear instability, while remember the Gregory-Laflamme mechanism was a linear instability. So a nonlinear instability is typically regarded as being more subtle and more difficult to capture via, if you want, it's more difficult to capture through numerical simulations. So if you want, is that kind of instability that is usually more easily captured through a rigorous argument, or if you want, through a mathematical theorem. And our new instability is already manifest at the level of scalar perturbations, while the Gregory-Laflamme mechanism is a genuinely gravitational effect. So it occurs when you look at matrix perturbations. And because because the new instability already occurs at the level of scalar perturbations, one might regard this new instability as being, if you want, more fundamental. And to end the second part of the talk, let me also stress that some very thin black rings might, I think, in principle, be affected by both the instabilities. So for both the regular Flamming instability and my new instability, there's no sharp description of which members of the black ring family should be affected by the instability. So there might be some overlap between the two phenomena. Okay, so this is the end of the second part of the talk. Are there any questions? Okay, so let me move to the third part of the talk. So the third part of the talk will be about the claim that this new black ring instability may be understood as a manifestation of a more general instability. So we'll try to make sense of this statement. So to do that, let me first go to a related problem, namely that of stability or instability of current gas black holes. So that these are black hole solutions to the vacuum Einstein equations with negative cosmological constant. So current gas black holes, when one assumes reflective boundary conditions, they turn out to admit stable trapping. Okay, and because of the presence of stable trapping, one has the following result by Oelsegel and Smule-Vichy. So linear scalar perturbations of current gas black holes, once reflective boundary conditions are assumed at infinity, decay slowly, meaning logarithmically, in time. And this theorem by Oelsegel-Smule-Vichy motivates the following conjecture that current gas black holes with effective boundary conditions at infinity are non-linearly unstable. Okay, and there's been some recent breakthrough result by Moschidis in the case of this conjecture restricted to pure gas spacetime as a solution to the Einstein-Blasov system. So here you should note the analogy with the logic of what I told you before for black rings. So you look at a certain spacetime, in this case current gas, you know that there exists stable trapping on the current gas exterior. Because of the presence of stable trapping, you're able to show the linear scalar perturbations decay slowly in time, and this allows you to expect that this family of spacetime should be non-linearly unstable. Okay. So stable trapping has also been observed for other geometries, like for instance microstate geometries, gravitational solitons, or ultra-compact neutron stars. And because of the presence of stable trapping on all these spacetimes, slow decay for linear scalar perturbations has been established. And because of this slow decay, all these spacetimes are conjectured to suffer from the same kind of nonlinear instability that I explained for black rings. Okay. Now looking at all these diverse geometries admitting stable trapping and for which linear scalar perturbations decay slowly in time, one might expect that the slow decay of scalar perturbations in presence of stable trapping is a more general and, if you want, a universal phenomenon. Okay. So I claim that one should expect that for very general stationary spacetimes, the mere existence of stable trapping implies that linear scalar perturbations cannot decay fast in time, and thus is suggestive of a nonlinear instability. Okay. Note that here one really should think that the spacetime can be very, very general. So one wouldn't need to assume anything on the asymptotic structure of the spacetime, or if you want anything about the explicit algebraic form of the matrix, the symmetries of the spacetime, the number of dimensions, and you wouldn't even need to assume that the spacetime possesses a black hole region or solves even the Einstein vacuum equations. So the claim should really be that, considering very general stationary spacetime, if you can observe stable trapping on on the space-time, then linear scalar perturbations should be forced to decay slowly in time, and thus the space-time should be expected to be non-linearly unstable. So as a particular case of this, if you want, of this expectation, all stationary solutions to the Einstein vacuum equations, where the cosmological constant, again, doesn't need to be assumed to be positive, negative, or equal to 0. So all stationary solutions to the Einstein vacuum equations, which admit stable trapping, may be conjectured to be non-linearly unstable as solutions to the Einstein vacuum equations. So this really should be seen as a universal phenomenon. And such phenomenon is universal because the mechanism underlying this slow decay is itself universal. And remember, I told you that this dispersion in stable trapping is driven by the tunneling effect. Okay, so the mechanism driving this slow decay is a local tunneling effect happening in proximity of the minimum of some effective potential, like the one that I showed you before in the picture. So the global, if you want, structure of the effective potential will depend on the particular spacetime the one considers. But since this local tunneling effect always happens in proximity of the minimum of the potential, the global structure of the potential will not really play a role. And that's why this general discussion of spacetime is expected to be general, because the phenomenon driving the instability is a local phenomenon. And the quantitative statement that I also told you about, namely the logarithmic decay in time, is also universal. And this comes from a quantitative aspect of the tunneling effect, namely the fact that the tunnel energy of a trap wave the energy of the wave will tunnel through with some exponential rate in frequency. And this is what determines this logarithmic lower bound that I told you about. Okay, so let me remark that in hindsight, stable trapping is the only truly fundamental property of very thin black rings for the new instability to arise, while their other global spatial algebraic properties are not in principle crucial. And this should be again in contrast with the Gregory-Flaming stability, which more heavily relies on some global properties of the spacetime. So in view of this more general picture, one should expect that this new instability affects some other higher dimensional asymptotically flat spacetimes for which slow decay hasn't been established yet. So one example is very thin, but now doubly rotating 5-dimensional black rings. And another example could be also some ultra-spinning objects, like for instance, ultra-spinning Milesperry black holes in 6 dimensions. So maybe this is maybe more like for people familiar with this kind of spacetimes. But this instability should also appear for asymptotic Kaluza-Klein spacetimes. So this instability is expected to affect all 3+1 dimensional Schwarzschild black strings. So in the case of the Gregory-Flaming stability, the black string is required to have the size of the extra dimensional black string should be larger than a certain critical value. So meaning that black strings with very small compact extra dimension are not affected by the Gregory-Flaming stability. While in the case of this new instability, really all black strings, meaning without restriction on the size of the extra dimension, will be affected by the new instability. While the new instability also somehow distinguishes between 3+1 dimensional black strings and higher dimensional black strings. So black strings, n+1 dimensional black strings, when n is greater or equal than 4, will not be affected by the new instability, because these higher black strings that don't admit stably trapped null geodesics. Okay, and this should be seen as an analogous of the statement that higher dimensional Schwarzschild black holes don't admit stable time-like circular orbits. While on the other hand, the Gregory-Flaming stability also occurs for higher dimensional black strings. Okay. And so the instability will also appear for all 3+1 per black strings and for more general spacetime known as p-branes. They are obtained by multiplying the 3+1 dimensional Schwarzschild and 3+1 dimensional curve by more than one compact compact extra dimension. Okay. Let me maybe briefly summarize what I said, and then I'll stop. So I told you that we should expect a new nonlinear instability for black rings. So I told you that this black ring is supported by mathematical theorem that we can rigorously state and prove. This is a nonlinear instability coming from slow decay of linear perturbations, and it already occurs at the level of scalar perturbations. So it can be ascribed to a precise geometric property of black rings, namely stable geodesic trapping, and may be understood as a manifestation of a more general instability, which extends the expectation for this instability to appear for other higher dimensional black holes and for other more general and different geometries. Yeah, I think I should. Yeah, I think I'll stop here. Thank you very much for your time, and I'm of course happy to answer some questions.
Thank you, Gabriele. And we have a few minutes for questions. Please raise your hands. And yes, Alex.
So just to check I understood once again, the point is that in Kerr, there's this photon shell, but because the orbits are unstable, then that doesn't spoil the stability of the space-time.
Right.
But you're saying that if the space-time does have stably trapped geodesics, null geodesics, then you can expect it to be unstable.
Yeah.
So somehow these two things go hand in hand.
Yeah. I mean, of course, to prove decay, you need more than just, improving decay. Understanding the structure of trapping is one element in improving decay. But what is true is that if you observe stable trapping, then you should expect that if you can prove decay, then decay won't be fast.
I see.
While in presence of unstable trapping, that's in principle compatible with being able to prove fast decay. So you could have a space-time where you have unstable trapping and maybe you cannot prove decay. But the claim is that if you have a space-time where you have unstable trapping and you can prove decay, this decay can in principle be fast.
That's a very interesting connection. Thank you, Gabriele.
Any other question for Gabriele? No, doesn't seem so. So let's thank Gabriele again for a very interesting talk. And next week is actually Harvard Wellness Day. So we won't have a Zoom next week. So we'll see you all in 2 weeks from now. Thank you.
Thank you very much.
Thank you.
Bye-bye.